Hello everyone, welcome to lecture 22. So today we're going to pick up where we left off on rolling without slipping, and today's basically going to be all about conservation of energy in rotational motion. So as a quick reminder, where we left off in the last lecture was rolling without slipping. So in general, an object can move, translate, and rotate at the same time. This term, rolling without slipping, is the very special property where translation and rotation match up to one another. So for example, if I have a ball rolling down a hill, if the amount of distance it goes s is equal to r times the angle theta that it rotates, or velocity is r times omega, a equals r times alpha, we would call that rolling without slipping. The cool thing that this enables is that the point in contact with the ground is at rest. The velocity is instantly equal to 0, which is what we showed last time. So that means we have static friction. Static friction is a conservative force. And so the last thing that we showed at the end of lecture last time was that rolling without slipping involves energy conservation. All right, so we left off having shown that with this example of two spools, or a single spool wrapped two different ways. So what we saw was that if we take the spool and we pull it from the top, part A here, the object, not surprisingly, is going to move to the right. And then maybe a little bit more surprisingly, if we have it coming off the bottom, which is part B shown in this slide, that also is going to move to the right, and not, as some might expect, it's going to unroll to the left. So we're going to start off today by actually solving this example using the properties of rolling without slipping. And then we'll actually talk about how we can make this guy go to the left in kind of a similar manner. Alrighty, so let's start off by solving this problem. Part A looked as followed. I had a spool. Mass of the spool was M. I didn't specify. Let's say its moment of inertia is just some I, which again I'm going to just treat as a number. And what we did was we had a force coming off the top here, pulling it to the right at radius r over 2. And the total radius from the center of mass out to the outside is r. Okay, so that's our setup. And now the first thing we always want to do in these types of problems is draw the free body diagram. So what other forces besides F act in this problem? Let me redraw this for a free body diagram. Okay, so we'll start off, we'll draw F. Acts to the right at radius r over 2. The spool has weight, so that weight is going to act at the center of mass. It's in contact with the floor, so there will be a normal force. Let's call it N from the floor. And then there's one other force in this problem. So hopefully you've guessed it's static friction. And here it's static because it's rolling without slipping. So static friction, we're going to guess it acts to the left, and then we're going to check our answer. So if our answer ends up being negative, that'll tell us we were wrong, and in fact it acted to the right. Alrighty, so here are all my forces. And again, remember that when we do rolling without slipping, we want to consider translation of the entire object, and we want to consider rotation around the center of mass. So the axis of rotation is just going to be the center of mass here. We'll do our usual thing, introduce coordinate axes, x, y as usual, z as usual is going to be out of the plane. And now we use Newton's laws. So let's start out with the total force. The total force in the y direction, for what it's worth, is 0 because it doesn't accelerate up or down. That's just n minus mg, which is going to give us our usual thing that n is equal to mg. Not all that exciting. The total force in the x direction is going to be capital F in the positive x direction minus force of static friction in the negative x direction, and that is equal to the mass of the object times its acceleration, in the x direction. And finally, torque. Since this is an object with rotational motion, the total torque in the z direction. So which of these forces is going to cause torque? All right, so gravity does not, because it acts at r equals 0. It acts right at the axis of rotation. The normal force does not, because it's parallel to the radius vector. So it doesn't cause any torque. This force that we pull on is going to cause a torque, and static friction is also going to cause a torque. Now, rather than making this complicated, let's just figure out their signs by figuring out what type of rotation they want to cause. So force capital F, does that cause clockwise rotation or counterclockwise? I should say acceleration. So you can see F wants to make it rotate clockwise. And that's a negative torque in the z direction. So the torque is negative F times r over 2 because it's perpendicular to the radius r. So you see that this is perpendicular to the radius at which it acts. Okay. Similarly, does friction want to act in the positive? Does it want to cause counterclockwise rotation or clockwise rotation? So as I've drawn it, friction is going to cause also clockwise rotation, which we know is negative z. So it's minus Fs, and that acts at a radius r, so it's minus Fs times r, again, because it's perpendicular to the radius vector. So we can add these guys up. We get that the net torque is negative Fr over 2 minus Fs times r, and that again is I times alpha. Okay, so I have two equations relating our forces to our accelerations. We don't have enough information to solve this problem quite yet. So force of static friction is an unknown, acceleration is an unknown, and angular acceleration is also an unknown. So two equations, three unknowns, that's a problem. What other information are we going to use that's going to help us to solve this problem? So we still need to use the fact that this guy is rolling without slipping. We kind of used it because we used the fact that it's static friction. But now we're going to use the other very important property of rolling without slipping, that distance is connected to angle. So we know S is equal to r times theta. We know that the magnitude of velocity, or the speed, is equal to r times omega. And we know, let me just say omega, the magnitude of omega. And we know that A is equal to r times alpha. So here, of course, A and alpha are what we're going to use. Now, I want you to be careful when you're using this law, because this just tells me that the magnitude of acceleration is proportional to the magnitude of alpha. We still need to be careful about the signs. So here, what I want to consider is, for example, if AX is positive, as we expect it to be here, so if it starts to accelerate to the right, will that cause clockwise or counterclockwise rotations? CC, counterclockwise. Sorry, just saving some time. So as you see here, if it starts to move to the right, that's going to rotate clockwise, exactly like what our forces were doing. And we know that that is actually negative alpha. So when acceleration, linear acceleration is positive, alpha is negative. Alpha z is negative. So what that tells us is that A, in this case AX, because that's the only acceleration, is equal to negative r times alpha z. So always be careful about the sign of the relationship between acceleration and angular acceleration. Okie dokie, but now we have three equations and three variables, and we simply need to go forth and solve. The first part of this problem asks us What is the resulting acceleration? In fact, that's all that it asks us for. So let's eliminate everything else from the problem. First, let's solve this equation for alpha z. Alpha z is equal to negative ax divided by r. Let's plug that in to the torque equation. So if I plug that into the torque equation, I get negative capital F r divided by 2 minus Fs times r is equal to I times alpha, that becomes I times negative ax divided by r. All these negative signs cancel each other out. And now if I want to solve for my force of static friction, what I will do is I will bring capital Fr over 2 to the other side. So now this is all just algebra. We've done all of our physics. We have Fs times r is equal to Iax over r minus Fr over 2, capital Fr over 2. Divide everything through by r, and I get the force of static friction is Iax over r squared minus F over 2, capital F over 2. Finally, I plug this into my Newton's law, the force equation. So the total force is just capital F minus Fs is equal to, now if I plug this equation in, that's F minus Iax over r squared plus capital F over 2 is equal to mass times acceleration, max. I want to solve for acceleration, so let's bring this guy over here. Combine the two terms, I get 3F over 2 is equal to ax times m plus I over r squared. And when I divide through by m plus I over r squared, my acceleration is equal to 3F over 2m plus I over r squared. And importantly, as expected, this is positive. All of these numbers are positive, so this guy is positive, meaning it moves to the right. So that's not surprising, but it's good, to see what we expect. So now let's talk about part B. Part B, I'm now going to pull at the bottom, and not all that much changes. So now if I draw out my free body diagram, looks very, very similar. So I still have gravity pointing down. I still have a normal force pointing up. I still have friction, which I'm going to guess points to the left, but again, we won't really know until we solve it. And now the only difference is that my capital F is acting down here at the bottom. So for instance, if I do Newton's laws, the total force in the x direction, nothing changed. It's capital F to the right minus Fs to the left is equal to mass times acceleration. But now my torque has changed. So let's talk about the total torque in the z direction. Fs times r hasn't changed. That still causes clockwise rotation, and therefore it's negative Fs times r. But now let's take a look at this capital F. Does that now want to cause clockwise or counterclockwise rotation? So it wants to cause counterclockwise rotation, meaning that's plus Fs, capital F times r over 2. And where the intuition on this problem breaks down is that seems like it wants the object to move to the left. Okay? So static friction seems to want the object to move to the right. Friction, this capital F seems to want to move it to the left, but actually if you look at the Newton's laws, it's exactly the opposite rule. So it's a little funky. And there's really no magic here. We just have to solve the equation. So here, I'm going to go ahead and do it. It's the same bit of algebra. So first off, it is still the case that A is equal to alpha times r, negative alpha times r. So in other words, this is negative Iax over r, just like before. And now let's go ahead and solve for this. So I'm going to start by actually solving for static friction in the force equation. So this force equation gives me static friction is equal to capital F minus mass times acceleration. And then I'm going to plug that in to my torque equation. So I get negative capital F minus mass times acceleration times r plus capital FR over 2. Notice that this is now a positive sign. That's the only difference. Is equal to negative IAX divided by r. Got this annoying r in the denominator, so let's just multiply everything by r. And now I'm almost good to go. So let's go ahead and write out all these terms. I have negative FR squared plus MR squared AX plus FR squared over 2 is equal to negative IAX. Bring the AX terms over to the left-hand side. Bring the FR squareds over to the right-hand side. I get acceleration times I plus MR squared is equal to positive FR squared over 2. And now when I solve for acceleration, it's a third of the previous value, so my acceleration now is FR squared over 2 times I plus MR squared. Previously it was 3FR squared over 2M I plus MR squared. This is the same thing, just I've brought the R into a different location. But again, it's still positive. It's a little less, but it's still positive because all of those numbers are positive. So the kind of key takeaway from this example is write down your forces, write down the torques, use Newton's laws exactly as I've taught you. And then when it's rolling without slipping, S equals R times theta. You don't use that very often, but it's true. V equals R times omega. We're going to see that quite a bit throughout this lecture. And for this problem, A is equal to R times alpha. So make sure you use that connection and make sure you're very careful about getting the correct sign of the acceleration as compared to alpha. Okay, so the biggest mistake that I tend to see on these problems is either forgetting to do it at all or making a sign mistake when you're connecting A to alpha. So there we go. That's basically the physics we're going to be after in this. And now we're just going to do a ton of examples, seeing how this works out. Sorry. My computer doesn't seem to want to go to the next slide. Let's see if we can get it to do it. All right, we'll do it the old-fashioned way. All right, so here's our next example. Two blocks of mass 5 kilograms and 10 kilograms are connected over a massive pulley which has mass 7 kilograms, radius 0.2 meters. And since it's a cylinder, we'll say that I is a half mr squared. The strings move over the pulley without slipping. So there's one thing I want to tell you before we solve this example. For pulleys with a finite mass, it will no longer be the case that tension is constant throughout that spring. Essentially what happens is that the tensions are going to create a torque on the pulley, which is necessary because the pulley has to accelerate. And if the tensions were exactly the same, the net torque would have to be 0. So you can think of what's happening is there's some static friction between the pulley and the string. That static friction is going to create torque, and is in the process going to make the tensions different. Okay, so here's our setup. We have the two blocks. We have our massive pulley, and for a massive pulley, the tensions on either side of the pulley are actually not the same. So using this information, I want you guys to write down the free body diagrams, do all the things we usually do, and see if you can tell me what is the velocity of the 10 kilogram block after it moves down 2.5 meters, and what is the acceleration of the 10 kilogram mass. Alrighty. So hopefully at this point you've had an opportunity to give this a shot. I'm going to try my fancy little bit of machinery that we can do here on my iPad. So let's go ahead and copy our pretty little diagram right here. See if I can get this. 1 in 10 chance this will work. Copy. All right, so now we can go over into our handy dandy PDF. And with any luck, I should be able to paste it. Oh, come on. No, well, can't win them all. All right, so here we go. Freehand drawing of the exact same thing. I have my massive pulley with 7 kilogram mass. I have 2 strings, which I told you have different tensions, T1 and T2. And they're hanging off them are 2 blocks, mass 5 kilograms, mass 10 kilograms. Since I love to introduce symbols, I'm going to call this M1. I'm going to call the 10 kilogram mass M2, and I'm going to call the 7 kilogram pulley capital M. Capital M is 7 kilograms. The radius of the pulley is 0.2 meters. And it's told to you in the problem statement the moment of inertia of that pulley is 1/2 mr squared. All right, so the question is, what is the velocity of the 10 kilogram block after it moves down 2.5 meters? And what is the acceleration of the 10 kilogram mass? So there are various ways to solve this. Option 1, which I'm not going to go all the way through, but I highly encourage you to work through if you like, is simply Newton's laws. So we can write down what's going on here. I have mass M1 that has gravity pulling it down, that has tension 1 pulling it up. I have mass M2 that has gravity pulling it down, that has tension pulling it up, T2. And finally, I have our pulley. So the pulley, I'm not going to bother with the axis itself. There's a normal force in the axis. There's a weight from the axis. We don't care about that since it's just rotational motion. The important thing here is the torques, and the torques are T1 pulling on the left side. So still, it will be the case that this tension acts like it's acting on the point where it leaves the pulley. That's the point of contact for the string. And similarly, we have T2 hanging off the other side. So we have these kind of pair of earrings. And those are going to cause a torque. And now we go through the little bit of math. Let's go ahead and set up Newton's equations. So I'll introduce my usual axes. Z is out of the plane. We'll go through one by one. So the total force on mass 1 is just T1 pointing up minus M1G pointing down. And that is equal to M1 times the acceleration of 1 in the y direction. The total force on 2 is equal to T2 pointing up minus M2G pointing down. That's equal to M2 times AY2. Finally, since the pulley is only rotating, all we're going to talk about is the torque. And by the way, those are both the forces in the y direction. Sorry about that. So let's talk about the torque. Notice that T1 wants to do counterclockwise rotation. So that's going to cause a positive torque, T1R. And T2 wants to create a clockwise rotation. So that's going to be a negative torque in the z direction, negative T2R. And that in turn is going to be equal to I times alpha. And now I just need to add a few constraints. So if block 1 accelerates up, then block 2 accelerates down, which tells me that AY1 is equal to negative AY2. And similarly, these guys are all rolling without slipping. So there's a connection between A and alpha. And now let's go ahead and be a little bit clear on this. If the acceleration of block 2 is positive, meaning block 2 is moving up, then alpha z is positive. It's counterclockwise rotation. So we can intuit that ay2 is equal to positive r times alpha z. Again, being a little bit careful about the sign. So here we go. These are all the equations. If you like, you solve these equations, you solve for the velocity of the block after it moves some amount of time, you will get the right answer. Absolutely 100%. This is completely valid and would be accepted on the exam, particularly since I no longer have long answer questions. So have at it. However, I'm going to, as always, show you the slightly easier way, which is to use conservation of energy. So for this problem, because all I care about, at least in part A, is velocity, in other words, kinetic energy, the better choice is to use conservation of energy. And so in particular, we're given an initial condition where everything is at rest. And for simplicity, I will call y equals 0 the initial height of these guys, because they're the ones that have gravitational potential energy. Technically, the pulley also has gravitational potential energy, but it doesn't move, so the gravitational potential energy is constant, and we could forget about it. All right, so initially, the potential energy is gravitational. U gravitational initial is equal to 0, because everything's at y equals 0. And everything's at rest, so the initial kinetic energy is 0, meaning if energy is conserved, the total energy at all times is going to be constant, and it is going to be equal to 0. Let's talk about the final state. So in this part of the problem, it asks what happens after the 10 kilogram mass, block 2, falls down by 2.5 meters. So at the end of the day, the final y value of block 2 is negative 2.5 meters. And since I like to introduce symbols, I'm going to call this negative h. On the other hand, if block 2 goes down by 2.5 meters, block 1 has to go up by the same amount. So YF1 is positive 2.5 meters, or positive h, which means our gravitational potential energy at the end of the day is going to be m1 g times positive h minus m2g times h, or plus m2g times negative h. So that's changed, which makes sense. That's why the block 2 is falling. What about kinetic energy? So what is our final kinetic energy? So for this point, what I want you to remember is that the final kinetic energy is simply the final rotational kinetic energy of all the objects plus the final translational kinetic energy. So I just add up rotation plus translation. Now let's talk about rotation first. Which of the objects is rotating? So it's just the pulley. The other objects are just falling. They're not rotating. The pulley is rotating. And so it has kinetic energy 1/2 I times omega z squared. Similarly, blocks 1 and blocks 2 are just translating. So they have kinetic energies 1/2 m1 times v1 squared, v1 final squared, plus 1/2 m2 times v2 final squared. And now, our little bit of magic here, because of rolling without slipping, we have that first off, well, these two, v1 and v2, if v1 moves up, if object 1 moves up, object 2 moves down at the same rate, so their speeds are identical. Their y components are opposite, but their speeds, which is all that matters here, are identical. And furthermore, their speeds are equal to r times omega z because of rolling without slipping. So now again, we're going to use this nice property that velocity is connected to omega. And so now when I plug that in to this equation, my kinetic final can be rewritten as 1/2, let's go ahead and write it out, I is 1/2 capital MR squared times omega z final. Well, that's just v, let's say v2 final over r squared, plus 1f m1 times v2 final squared, because v1 final is equal to v2 final, plus 1/2 m2 times v2 final squared. Or if I factor out the half v2 final squared, which is in each one of these terms, what I get is my final kinetic energy is 1/2 v final squared times m over 2, capital M over 2, plus little m1, plus little m2. That is my final kinetic energy. And now I just use conservation of energy. So my kinetic final plus gravitational final is equal to my total energy, which was 0. So the 0 is equal to simply m1 m1 minus m2 times g times h, that's gravitational, plus this expression for kinetic energy, 1/2 v final squared times capital M over 2 plus m1 plus m2. And now I'm simply left to solve for my final speed, v final, of block 2. Let's go ahead and do that. I'll bring the m1 gh over to the other side, multiply both sides by 2, so I have v final squared times big M over 2 plus little m1 plus little m2 is equal to 2gh times m1 minus m2. Divide both sides by m over 2 plus little m1 plus little m2. Just take the square root of both sides, and then I get v final is equal to the square root of 2gh times m1 minus m2 over m over 2 plus m1 plus m2. Annoying, but just algebra. At any rate, when you plug in some numbers, you find that this is 2.6, sorry, no, that's not right. Try again. You find that the velocity is, something that I did not write in my notes, but fortunately it's a very simple expression. So I can go ahead and go into Google, which I am doing, trust me, on a separate computer right here. So 2 times 9.8 times the height, which was, what did we say? 2.5 meters? 2.5 meters. Times the difference in the masses, that's 5. This, by the way, should have been m2 minus m1 because I brought it over. That should flip the sign. This has to be a positive number. Negative m1 minus m2. So 5 kilograms. All divided by capital M over 2. So I said it was 7 kilograms. So that's 3.5 plus 5 plus 10 kilograms. And the answer, lo and behold, is that the final velocity is, the final speed is 3.64 meters per second. Someone can check me on this. And since block 2 is moving down, the trick question I always like to ask, the final velocity of block 2 is in the y direction, and it's negative. It's moving down at 3.64 meters per second. So quickly, part B asks, what's the acceleration of the two blocks? Again, you could solve this one of a bunch of different ways. A trick that I kind of like is if you already know everything about velocity, then I also can just go ahead and solve for the acceleration. So what I know is that initially, block 2 had v equal to 0. Finally, and let's say y equals to 0. Finally, it had v final y2 is equal to negative 3.64 meters per second, as we just solved, and y equal to negative 2.5 meters. So now I can just go to the following equation if I want to solve for acceleration. Delta vy squared is equal to 2 acceleration y times delta y. So that says my acceleration in the y direction is delta vy squared. So vy final squared minus vy initial squared divided by 2 times delta y. So that's y final minus y initial. When we plug in these values into this equation, we get a negative acceleration, and its value turns out to be negative 2.65 meters per second squared. So if you had solved the problem using Newton's laws, you would have already had this. But if not, it's really not so bad. Just a couple of line calculation. So there we go. That is how to use conservation of energy with rolling without slipping to solve these types of problems. So now let's see a couple more examples of this. This is generally speaking the best way to solve the majority of these problems. Use conservation of energy. Here's a really good one that wants to use conservation of energy. A simple yo-yo is created by wrapping a light string, meaning a massless string, around a cylinder of mass 0.75 kilograms, radius 0.3 meters, to create a yo-yo. So starting at rest, imagine it falls a distance 1.5 meters and the string unrolls without slipping. So what I want you to think is, what is the final speed of the yo-yo's center of mass? How fast is it moving after 1.5 meters? And is it faster or slower than if I just drop the yo-yo without letting it rotate? So before actually solving part A, I want you to think, is it faster or slower when it moves here, if it rotates, or if I just drop it directly without rotation? Okay, so we'll come back to that using the language of conservation of energy. Take a couple minutes to solve this one. All right, so I'm going to go ahead and assume that you've solved this one at this point. Let's go ahead and go over the answer together. So going back to our PDF, here is my primitive yo-yo. And now I'm not going to even bother drawing a free body diagram. We're just going to use conservation of energy from the get-go. Okay? So from conservation of energy, I want to write an initial state, and I want to write a final state. So the initial state is what's shown in the figure. I have my yo-yo with an ideal string wrapped around it. It is not moving. Velocity initial is 0. Angular velocity initial is 0, using my usual coordinate system. Okay. What I do know is that the object has a mass, which I will call little m, equals to 0.75 kilograms. It has a radius, which I will call capital R, 0.03 meters. And in order to set a coordinate system, let's call y equals 0 my initial state. So y initial equals 0. And just make our life easier down the road. Again, it's never important what I call y equals 0. So let's say y equals 0 is the initial position of the center of mass. So now this is exactly like the previous problem. I've set it up so that my initial kinetic energy is 0 because it's neither moving nor rotating. And my initial gravitational potential energy is 0 as well because it's mass times g times y initial. And y initial is just 0. All right, so that's my initial state. My final state is after the yo-yo has fallen by a height h, which is equal to, what did I say, 1.5 meters. So now my yo-yo is falling. It has a velocity downward. This is not a free body diagram. I'm simply drawing the velocity. And it's rotating. And of course, you know that the rotation is going to be counterclockwise here because that's the way in which the yo-yo is unraveling. So we don't know either of these values, but we do know that they're connected. So in this case, is Vy positive or negative? Well, it's negative, right? It's moving down, so we know that Vy is negative. Is omega z positive or negative? So in this case, it's positive because it's rotating counterclockwise. So we know that V is equal to R times omega up to a sign. And now, because these guys have opposite signs, we see that Vy final is equal to R times omega z final. So you always, negative r times omega z final. So get that sign right, and you'll be a much happier camper. Rightio. So that is rolling without slipping. They're tied together. We've also used the fact that energy is conserved. So now let's go ahead and solve for the energy. Gravitational final is just mgy final, and y final is negative h. It goes down by h, so it's negative mgh. Our final kinetic energy for this rotating cylinder is again going to be rotational kinetic energy, 1/2 I of the cylinder times omega z final squared, plus translational kinetic energy, 1/2 mass times Vy final squared. Now plugging in what we know about these values, first off, moment of inertia for a cylinder, we use it time and again, 1/2 mr squared. Notice this is the same mass in both of these terms because it's the same object. The object is both rotating and translating, so it's going to enter both, the mass is going to enter in both the moment of inertia and in kinetic energy. And omega z final, we saw was negative Vf over r, but since we're squaring it, we don't really have to care. So this is just Vy final over r squared plus 1/2 mv final squared. And that's simply, notice the r squareds cancel. I have mv squared, I have mv squared, and then I just have 1/4 mv squared plus 1/2 mv squared. So in other words, 3/4 mv final squared. So that's kind of nice. These m's always, actually that's a very general property. These m's will always cancel. The slightly more general version of this formula, if I had not canceled this out, I could have just written this out. I could have left the I alone. What you would see is that I have 1/2 I over r squared plus m times v final squared. So that would be 1/2 plus 1 is 3/2 times 1/2 is 3/4. That's the more general formula. Okie dokie. So these are both the same thing. That is my final kinetic energy, my final gravitational potential energy, and I know that my total energy is just 0 because my initial energy was 0. So let's go ahead and add these guys up and set them equal to 0. I'll use the general formula because we're going to want to use that later. All right, so 0 is equal to gravitational, negative mgh, plus kinetic, 1/2, mv squared times I over mr squared plus 1. That's just the same thing. I'm just dividing out the r, the m. I want to solve for v final, so we'll go ahead and cancel out the masses here. We'll bring gh over to the other side, do a little bit of algebra, and I get that my final speed in the so let me just write this as v final, no y component, is the square root of 2gh over 1 plus I over mr squared. For our particular problem, this is the square root of 2gh divided by 1 plus 1/2. And if I want the y component, that's just downward. So the particular velocity is negative instead of positive. And now we go ahead and plug in some numbers, and it turns out the answer is it's moving downward at a speed of 4.43 meters per second. So the velocity is negative 4.43 meters per second in the y direction. All right, so pretty straightforward once you use conservation of energy. Now notice, part B, is this greater than or less than the speed if I had just dropped the yo-yo directly? So So you kind of know this answer intuitively, right? If I let go of a yo-yo, it takes a little longer to unwind than it would if I just dropped it. That means it's going a lot slower than if I had just dropped it. Intuitively, why is that the case using conservation of energy? So if you think a little bit about what conservation of energy means, it means that I'm translating all of this gravitational potential energy into the final kinetic energy. So if I talk about the yo-yo that's dropped versus the yo-yo that actually rotates, the kinetic energy is the same. It's just mgh. The trick is that in the case of the dropped yo-yo, all of that kinetic energy is translational. So all of it goes into moving downward. In the case where the yo-yo rotates, that kinetic energy is split between kinetic energy to help it go downward fast and kinetic energy to help it rotate. So less of the kinetic energy is going into translation. That means that it moves slower. If we want to see this mathematically, it's pretty straightforward. Of course, I just solve the problem. So if I simply solve the problem for a non-rotating yo-yo, that we know is just v final y is equal to negative root 2gh. So if it's not rotating, it's the usual thing. V is negative root 2gh, which is negative 5.42 meters per second. So indeed, it's moving faster because less of that energy is going into causing rotations. Good. So we have one more quintessential example of this, the example that I just keep coming back to, of this uniform cylinder of mass m and radius r on an inclined plane. And now this bad boy is going to roll without slipping. All right, so the question is, if it now rolls without slipping, what is the force of static friction, which we weren't able to solve for earlier? And after falling a height h starting at rest, what is the final linear speed? All right. So hopefully you've taken a couple minutes, pause the video, solve this problem. Let's go ahead and see what the answer to this is. And actually, surprisingly, it's going to be quite related to that yo-yo problem. All right. So let's go ahead and start off by part A. What is the force of static friction? So here we go. I have my ball, a cylinder on the incline. Mass m, radius r, the angle of this incline is theta. And as we've discussed time and again, there are only a few forces acting on this ball. Let me give myself a little bit more room. I'll just go ahead and draw the free body diagram here. Let's see if I can do this. Wait. It didn't work. Let's try again. Much bigger ball, so I can give myself plenty of room. So the forces that act on this object are gravity, normal force, friction, which goes uphill, and in this case, static friction, which goes uphill. And that's it. From this, previously, we were able to establish that the torque in the z direction is equal to Fs times r, negative Fs times r, because it creates clockwise torque, so that's a negative torque. And if we introduce our usual axes, I will not redo this derivation. It was done in lecture 21, the previous lecture. It's pretty straightforward. We usually just break this guy up into components, but what we did solve for is the total force in the x direction, which is down the hill. And we saw that that was mg sine theta. You can quickly sanity check this because if theta goes to 0, so if it goes flat, then there is no force in the plus x direction. So that makes sense. Minus the force of static friction is equal to the mass of the object times its acceleration in the x direction. And this is all we could do earlier. We solved for the acceleration and the angular acceleration. Now we have one additional piece of magic due to the fact that it is rolling without slipping. Namely, that acceleration is proportional to alpha. So in particular, we know that if acceleration is positive, as we expect, it's going to go downhill. Then the rotation is going to be counterclockwise, which is negative. So again, we see that the acceleration is negative r times alpha. For our usual coordinate system, this tends to be the case, but you will always want to check that sign piece by piece, because it's very easy to have this go wrong. All right, so here we go. 3 equations, 3 variables, and now we just need to do a little bit of algebra. So the algebra we're going to do is to solve for the force of static friction, and I'm going to do that in 2 simple pieces. First, I will solve the torque equation for alpha. So alpha z is equal to negative Fs divided by I times R. And then we're going to plug that into this second equation. So mg, give it 1 second. So mg sine theta minus the force of static friction, which we don't know, is equal to mass times acceleration. So that's mass times negative r alpha, using our without slipping rule. And that in turn is equal to, if I plug in alpha equals negative Fs over mr over IR, is simply equal to positive mr Fs over IR. The r's cancel. Ooh, I must have made a mistake here. Let's see. A is equal to r times alpha. Yeah, so alpha was Fs times r over I. So r's definitely shouldn't cancel. Sorry about that. And now if we go back and I do my math right, so that's m times negative r, negative m times r times alpha is negative Fs times r over I. The negatives become positives. But now the r's do not cancel, as they shouldn't. And finally, I want to solve for the force of static friction. So what I'm going to do is I'm going to bring static friction over the right-hand side of the equation. I get mg sine theta on the left is equal to Fs times 1 plus mr squared over I. And finally, dividing through by 1 plus mr squared over I, Fs is mg sine theta divided by 1 plus mr squared over I. An incredibly intuitive formula, I know, but it is indeed correct. So that's our force of static friction for what it's worth. I can do a little bit better because I do in fact know the I of a cylinder. So I for a cylinder is 1/2 mr squared. That means mr squared over I is 2. And so for the special case of a cylinder, this is mg sine theta divided by 1 plus 2 is equal to 3. Okay. Now, part B of the question asks, what is the speed of the yo-yo? Not the speed of the yo-yo. What is the speed of the cylinder after falling height h? And what I want you to notice is that this is exactly the same question as what we asked for the yo-yo. So we have energy conservation because we have rolling without slipping. We have an object falling height h. And importantly, it doesn't really matter that there's this normal force because the normal force doesn't do work, meaning it doesn't mess with the energy translationally. It doesn't create torque, so it doesn't do rotational work, as we'll think about more next time. So the n really isn't doing anything. This is kind of like the yo-yo flipped on its side. And so the actual answer is exactly the same as the yo-yo. The speed, v final, is just this formula I told you last time on the last problem. Root 2gh over 1 plus I over mr squared. 1 plus I over mr squared. Which again, for this particular version, where I have a cylinder, is for root 4gh over 3. Not particularly exciting. All right, so that's my final velocity. And the question is, what happens if I change the shape of my object? So we're going to go ahead and watch a video here, and I want you to try to make some predictions. For a more general object with moment of inertia I, which I wins? So we have a few objects that we know. We have a solid cylinder. I is equal to mr squared over 2. We have a sphere. So, it's the same thing, but it's 3D. About its center of mass, I is equal to, I think it's 2/5 mr squared, but don't quote me on that. It's in the notes, I just honestly forget. This is why I give it to you on the exam. We have a hoop. If all the mass is concentrated around the outside, a hula hoop going down the hill, that's mr squared. So if I put these guys down the hill, which of them is going to win? The answer is whichever one has the lowest moment of inertia, which in this case I believe is the solid sphere. Why is that? Well, let's think back to our intuition about the yo-yo. The yo-yo was going slower at the bottom because some of its energy was trapped in rotational motion. And if you think about the kinetic energy of rotation, that's just 1/2 I omega squared. So if I is bigger, more I, or bigger I, means that more of our energy is going into K rotational, and less of it is going into K translational. If we go back to our actual math, the formula, root 2gh, that's just a constant over 1 plus I over mr squared. So if I want to make VF large, I want to make this denominator small, meaning large VF, the winner, is the one with the smallest moment of inertia in units of mr squared. So you'll notice all these formulas, it's always some constant times mr squared. And so for that turns out to be the solid sphere. Now let's see a quick example of this. We have this nice YouTube video. I really do like this demo that the guy does. Not a big fan of last time, but this is pretty good. This has got the name of the demo guy for a reason. So he is going to do a mime style demo.
This is what we have to investigate how moment of inertia affects an
object's
acceleration and velocity as it rolls down a ramp.
Talk.
These two objects have the same mass, and these have the same mass. We also have a bunch of acceleration and velocity as it rolls down a ramp.
Good stuff.
These two objects have the same mass, and these have the same mass. We also have a bunch of different sized
spheres,
balls, along with some cans that are full of liquid and others that aren't.
All right.
The idea is you can ask your
student
student
versus hoop. Who wins? The cylinder, because the cylinder has a smaller moment of inertia. 1/2 mr squared is less than.
Think, predict, and then verify and explain which object they believe will roll down the ramp the fastest and why.
And there you go.
Always have this box at the end too to catch things, just in case they get by your hands.
Yeah.
Now this device is nice because it allows you to actually change where these masses are located. There's a thumb screw on the top of it as well, so that way you can actually secure it in its location. So play around with them and roll it down the ramp, and then you can make another adjustment and roll it down another time. So like I said, these are great and fun to play around with. Sometimes after rolling it down, the masses will move, so make sure to double check that thumb screw is truly tight, and that way it'll sit where you want it as it rolls down.
The center, because the moment of inertia is much smaller. It's mr squared, and the distance to those objects is very small. And so on. You can do this with cans of beans, you can do this with cans of soup, you can do this with spheres, you can find all those on YouTube. But the key point is the moment of inertia is actually going to determine how fast you go. All right. So there's one more example I want to go through today, that of a seesaw. So far we've been talking about one really important example of conservation of energy, known as rolling without slipping. And let's say 90% of the problems that I like to give that involve conservation of energy with rotations are that. They are rolling without slipping or very, very similar things. However, there are other ways to conserve energy, and here is a good example. So imagine an unsuspecting student sits at rest on a seesaw when the heaviest man in the world, or at least he was the heaviest, and then he got stomach stapling surgery, but as of when this problem was created, the heaviest man in the world, Juan Pedro Franco, 590 kilograms, sits on the other end at rest. The seesaw is mass 15 kilograms, length 4.5 meter, and sits on a frictionless pivot 1.3 meters off the ground. So obviously the student's going to get launched in the air. The question is, what is the student's speed when the seesaw kind of hits the ground? Okay, so hopefully you've taken a couple minutes to solve this problem. Again, we'll go over the answer, and it's not too bad. This is another case where just using a little bit of conservation of energy is going to go a long way. So the reason that we can use conservation of energy is because the pivot is frictionless. There are no non-conservative forces in the problem, so energy is conserved. And therefore, all we have to do is specify an initial condition, specify a final condition, and that's it, really. All right, so initially, my seesaw looks like this. The pivot is halfway along, and I'm going to call the pivot point y equals 0. The lever itself has its center of mass right at the pivot point, so we're not going to have to care too much about the lever's gravitational potential energy, because that's not going to change. What is going to change is the student. So the student sitting at the other end, the mass of the student is 70 kilograms. The initial y value of the student is negative h, or negative 1.3 meters. And the student starts at rest, so the initial kinetic energy of the student is 0. And then we're going to talk about Juan, who's up here at the top. His mass, 590 kilograms, or about, 1,200 pounds, something like that. His y value is positive h initially. And his initial kinetic energy is also 0. He starts out at rest. So initial kinetic energy is 0. Nothing's moving or rotating. Initial gravitational potential energy is mass of the student times gravity times negative h plus mass of Juan plus times gravity times positive h. And then final at the end of the day. So at the end of the day, Juan's on the ground, the student's up in the air. And now they are moving. So here's my final end of the day. Here's Juan, y final of Juan. Give it a second. Y final of Juan is negative h. Y final of the student is positive h. And we don't know their velocities offhand, but we're going to solve for them. So the pivot stays put at y equals 0. That's why we don't have to worry about gravity on the lever. Notice if the pivot wasn't at the center of mass of the lever, then we would have to worry about the gravitational potential energy of the lever itself. Alrighty. So at the final end of the day, our final gravitational potential energy is mass of the student times gravity times positive h, plus mass of Juan times gravity times negative h. And now the final kinetic energy. So the final kinetic energy has 3 components. It has the speed of Juan, it has the speed of the student, and it has angular velocity. So these guys are both moving together, and they're both moving with the rotational motion. So because they're moving together, the speeds of the student and Juan will be the same. And as with rotation without slipping, they're going to be moving with the rotation. So we have omega z, we go final student, omega final Juan, is omega z times r, where r is the radius between this pivot and the endpoint. R in this case is given in the problem as, let me double check, 4.5 meters is the length. So the radius here is L over 2, 2.25 meters. All right, so now if we go through, our final kinetic energy is 1/2 mass of the student times the speed of the student, plus 1/2 mass of Juan times that same speed squared, plus 1/2 the moment of inertia of the rod times omega squared. And now let's go ahead and plug in the information we know. So these first two terms, I've already done that. This last term, what's the moment of inertia of a rod of length L, pivot around its center of mass? Well, you can look it up. It's 1/12 mass of the rod, which I'm going to call, the seesaw, which I'm going to call capital M, times length squared. So we'll treat it as an ideal thin rod where L equals 4.5 meters is the length. And that's multiplied by omega squared. But remember, omega is just velocity divided by r. So there we go. We're almost done. I'm going to do a little bit more math here. L divided by r is 2. Length is twice radius. So L divided by r squared is 4. When I write that out, what I get is 1/2 ms vf squared plus 1/2 mj vf squared plus 1/2 times a 12th times 4, that's a third, so that's 1/6 mass of the rod times vf squared, and that's my final kinetic energy. Alrighty. So finally, I'm going to use conservation of energy, which is pretty straightforward at this point. My initial energy is gravitational only. So that's mj minus m students times g times h. And that's equal to my final gravitational potential energy, which is just negative this. So that's m students minus m1 times g times h, plus kinetic, which is 1/2 vf squared times ms plus mj plus 1/3 of the mass of the rod. And now we're almost done. We simply need to solve for v final squared. I will save you guys 2 steps of algebra. Basically bring this guy over to the other side, multiply through by 2, divide through by the sum of the masses, take a square root. And what I get is v final, the final speed of the student, is the square root of 2 times 2, because there are 2 of these guys, so 4 gh times mj minus ms divided by ms plus mj plus 1/3 of m. Plug in some numbers, and it turns out it's actually not so crazy. At the end of the day, he's moving at 6.31 meters per second. I think that's about 15 miles an hour. So not fun. It'll go up a little, but, you know, he's not going flying over to the next county or anything like a cartoon. Alrighty, so that's basically what I wanted to say today. The big rule of thumb that I want you guys to keep in mind is when you see rolling without slipping, that should immediately trigger something that says conservation of energy. And even in problems like this with a frictionless pulley, where gravity is changing, where heights are changing, something like that, energy is conserved. You're going to use conservation of energy, and you're also going to be very careful to use this principle that V is equal to R times omega, A is equal to R times alpha, and make sure you get those signs right if you want to get the right answer. So that's all I have for you today. I hope you enjoyed this lecture. We're now caught up on rotational kinematics, lectures 21, 22. Homework 10, I believe it is on this material. It is due on Monday, so we're back on track. And I will see you guys early next week on Tuesday with a lecture on angular momentum.